All right, scientists, this is our last video for the proof of practice. So this one is on calculating energy and energy conservation. So on our picture, we see a roller coaster, we see point 1, we see point 2, and then we have data about it and we are to calculate its energy. So I'm going to zoom in here so that you can see the data and the energy a little bit better. We don't need the picture of the roller coaster anymore. Okay, so I have my my three formulas that go with my three energies. So we're just going to do point 1 first. So kinetic energy is 1/2 times mass times speed squared. So I'm looking for speed at point 1, and I'm looking for the mass. So I take 1/2 times my mass, which is 300 kilograms, times my speed at point 1, which is 100 meters per second, and then I need to square it. So if I'm going to do this in order of operations, I need to do my squaring first. So on this, I have 100 times 100. That's how we square. We take it times itself. So that's 10,000. Then I'm just going to bring my 300 down. I'm going to change my fraction into a decimal because I like that better. So I can take 1/2 times 300 times 10,000. So I take 0.5 times 300 times 10,000 equals. I get my kinetic energy at point 1 is 1,500,000 joules. So I need to know that that goes with point 1. Okay, so now I need gravitational potential energy at point 1. So I know that gravitational potential energy is weight times height. So I take my weight, which is 9,800 newtons, times my height at point 1, which is up here now, 122 meters. So all I need to do, there's no order of operations on this one. That's pretty nice. So I take 9,800 times 9,800 times 122, and I get gravitational potential energy at point 1 of 1,195,600 joules. So now I know that this is my gravitational potential energy at point 1. Then I need my mechanical energy at point 1. So I take the kinetic that I found, 1,500,000, plus my gravitational potential, 1,195,600 joules. I should add my unit over there and be a good role model. So my mechanical energy, and there's no order of operations, I'm just adding, is 1,500,000 plus 1,195,600 equals 2,695,600 joules. Okay, now I'm going to do the same thing at point 2. I'm going to switch to red so that you can see the difference. So kinetic energy is still 1/2 times mass times speed squared. So I'm going to rewrite that with filling in my numbers. 1/2 times my mass. My mass has not changed. It's still 300 kilograms. The only thing that's changed is my speed at point 2 is up here, and that is 40.47 meters per second, and I need to square that. So again, order of operations, I need to times 40.47 by itself, since that's how we square things. So I take 40.47 times 40.47. And I get 1,630. We'll round that up to 8. So I get 1,638 meters per second squared. I just square my unit. Sorry if that's confusing. We didn't get a chance to talk about that, so I'm not overly concerned. Times 300 times, I'm going to change that again into a decimal. So now it's all multiplication, so I have order of operations, just go left to right. So 0.5 times 300 times 1,638 equals kinetic energy at point 1 is 245,700 joules. So then I can box that. All right, then I need gravitational potential at point 2. So I need my weight times height. My weight has not changed. 9,800 newtons times my height at point 2 is 250 meters. So if I do 9,800 times 250, I get gravitational potential energy equals 2,450,000 joules. Okay? Then I have mechanical energy at point 2. So I add my kinetic from point 2 to my potential from point 2. So I take my 245,700 joules and I add it to my 2,450,000 joules. And if I do that, 245,700 joules plus 2,450,000, oh, forgot a zero there, 1,000 joules equals my mechanical energy of 2,695,700 joules. Now, you'll notice that my 2 joules are very close, 0.1 and 0.2. They're really just a 600 and a 700. And where that probably comes from is over here where we rounded on this 8, right? It was actually decimals, and if we had kept it as decimals, this would have gotten much closer. So for our purposes, these 2 numbers are constant. So what that means is, if we look here, at point 1, I have far more kinetic energy than point 2. And hopefully that makes sense, because at point 1, I have higher kinetic. I'm moving faster than when I'm at the top of a loop. And my gravitational potential at point 1 is much lower than my gravitational potential at point 2, which again, hopefully makes sense because my 2 is higher, so it should have more gravitational potential energy. However, my mechanical energy is essentially the same at both spots. And that's what this bottom one is asking, and that's what the last question that Ms. Sackett and I had to grade manually asked. Why is the mechanical energy constant in the picture? Mechanical energy is constant because it combines gravitational potential energy and kinetic energy. When one is more, the other is less. That's that inverse relationship that we talked about. Also, the law of conservation of energy states energy can't be created or destroyed. So the total energy, which in this case is my mechanical because it adds both of them, is the same at both spots. Okay, so I am going to, on the form, ask you questions about calculating and ask you questions about why it stays constant. Okay, so if you need to pause and look at this, let me get this in a good spot here. Please feel free to do so. Thanks, everyone.